All right, so we'll get started. I think we finished magnetism last time. So from today on, we are going to change the topic a little bit. We are going back to chapter 16. We finished the first part of chapter 16 last semester, oscillation motions. So the focus here will be on the waves, the later a few sections here in this chapter. And then after this section, we'll be looking into after this chapter, we'll be looking into the next chapter on sound. Okay, so wave and sound, uh, we put them under one topic, and then the last topic of the semester will be on optics. Okay, all right. So homework is due Tuesday next week. As I mentioned, we have finished magnetism, so you should be able to finish all the problems there. Um, and then exam 3 will be after the break when you guys come back. Okay, on Wednesday there. For the in-seat folks, I asked Jalen and Ethan for disinfection of the class. All right, so let's get to the chapter 16 section, I think section 9 here on waves. Okay, so think you guys have a lot of experience with waves. You can create a wave in the pond, just dropping a stone there. You'll see that. And then a few years ago, you probably heard about this, the gravitational wave being first detected. It was proposed by Einstein many years ago, but it was first detected only in recent years. All right. So we'll be looking at waves today. Um, so if you've been going to a large ball game, so people like to make wave, right? Or if you go to surfing, you'll see there's a wave there. And then as the person is in the ocean, it will be also carried by wave in that sense. Okay, so the question is, do you actually travel along with the wave in the same direction? So the answer is no, right? So if you are making a wave, you are just for example in the sports game here, you just go up and down in your seat, but the wave go in the horizontal direction. Okay, so you are going up and down, the wave go in the horizontal direction. You don't travel along the wave in the same direction. Rather, you are perpendicular to the direction of wave is traveling. Okay, in this case. So these are one type of wave. Okay. And then there's another type of wave there. So the focus on this chapter will be on mechanical waves. Okay, so let me just be clear with that. So they are mechanical waves, they are electromagnetic waves, okay, and they are like magnetic field, the gravitational field waves, etc. So the focus on this class will be on mechanical waves, okay? So first, let's take a look on some of the terminologies, or rather review some of the terminologies, okay? So for waves, if a peak goes, wave peak goes from one peak to the next peak, then the path it takes, or the distance traveled is called the wavelength. We use lambda, and the wave will have a magnitude. That means the maximum displacement from the equilibrium position. We call it amplitude. All right. And there's a time it takes from one peak to the next peak. It's called a period. So the speed then is defined by the distance traveled divided by the time of period. So lambda divided by t, they'll be giving you the speed of wave. Okay. And if you do 1 over t inverse of period gives you frequency, so then wave can be equal to, the speed of wave can be equal to also frequency times lambda, okay? All right. For the sound, this is the speed we might be using so often, so it will be beneficial for you to memorize that. Speed of sound in air at room temperature is around 340 meters per second, okay, or roughly 770 miles per hour. So it's more useful to remember this number in the SI units, 430 or 340 meters per second. Also, okay. All right. So for mechanical waves, there are two types of waves. mechanical waves. One is called transverse wave, and then the other is called longitudinal wave. Okay, in the case of the transverse wave, the wave is going in one direction. The media carries the wave will go in the direction perpendicular to it, so going back and forth. All right, so that's called a transverse wave. All right. Now for the longitudinal waves, in that case, if the wave is going in this direction, the oscillation of the media is in that same direction, okay, in that same direction. So, but just going back and forth, the media doesn't go along with the wave, it go back and forth, okay, but the vibration is in the same direction, okay. If this is horizontal, it's also in horizontal, okay. So those type of waves are called longitudinal wave, okay. To give you an example, for a guitar, if you play guitar, when the strings are vibrating, so there's a wave in the string, that wave is called the transverse wave because the wave is going along the direction of the guitar string, but the vibration of guitar string is perpendicular to the string. So that's a transverse wave. However, the sound of the vibration of guitar string makes is then a longitudinal wave. That's the sound wave because the sound wave propagates in this direction. The media carries sound wave is air. Air will be being pushed back and forth, okay, in the same direction that the sound wave is propagating, okay. So sound wave is a longitudinal wave, okay. All right, so that's that section. Let's give our general definition for the two types of mechanical waves, all right. So if you have two or more waves, when they meet in space, they will interact with each other. Okay, so as this is called superposition and interference. So if you have wave y1 and another wave, we call it y2, when they meet in the same string over here, so then they will just add up algebraically. Okay, so if you send two waves, y1 and y2 in the same string, then you will see two waves there. Okay. All right. And then if you have two identical waves, you send them into the same string in the same time, then they will add up. Okay. So if you have amplitude of vibration of media to be like x, they're identical. So then the result will be two times of that. Okay. When they add, when the two waves add up, we call it constructive interference. When they actually cancel out, we call it destructive interference. Okay, so in this case, if you send two waves, wave one and wave two, when wave one have maximum, wave two if it has the other the displacement maximum in the other way. So those two will cancel out because positive and negative. Okay, so then the resultant will be just total the cancellation of the two waves, okay, because they are the same waves but with a phase shift. We call actually this as with a phase shift. Okay. All right. So this is called destructive interference of two waves. In general, you might have two different waves, okay, and then they do not add up completely or they cancel out completely. So they'll just add up algebraically, okay. So for these two, if you have them in the same media, you send them into the same media, this will be the resultant, okay. So basically, again, it's the algebra sum of this wave and then this one, okay. When the two waves they meet again in the media. So for example, if this wave in the media is propagating in this direction, and then there's another wave propagating in the opposite direction. When the two meet, they add up. After they meet, they just go in the original direction of propagation. So the right wave now is going to the left, the left wave is going to the right. Okay, so they behave like they never met before after they met there. Similarly here, if you have a peak, a valley. This we call a valley here. If they meet, then they cancel out. But however, after they meet, they will just continue to propagate. Okay, just as act as they never met before. In that sense. All right. So those are like one-dimensional wave propagate in one-dimensional. Okay. Now, in reality, you will have wave propagate in two-dimensional or maybe in three-dimensional as well. So, for example, if you generate a water wave in a pond, it propagates pretty much in two-dimensional. Okay. So, if that happens for wave, if you have a peak, okay, then this is the line here, the solid line here in between. It's not showing, but it should have a valley, okay, the minimum or the minus of the amplitude there. So if you have two-dimensional wave meet, okay, they will superpose as well. So you can see if a peak meets another peak, then will add up. If a peak meets a valley, then will cancel out. Okay, so in this case, that's the cancellation of the two. And then this is the add up because peak meet peak, the lines are intersect. The other case is a line will meet a minimum in between the other wave. Okay. So if you will have the expression for the two waves, you can add them algebraically as well. Okay. And then there will be three-dimensional waves like electromagnetic waves. For a radio tower, it gives out electromagnetic waves. So that's propagated in three-dimensional. Okay. And gravitational waves, they are in three-dimensional as well. Okay. All right. Let's take a look if you have waves by two sources, source 1 and 2, okay? If they give out identical waves at the same time, so for example, this guy, if it gives out wave, okay, and then this guy gives identical wave. If they are starting with the same phase, that means they are having the peak at the same time and then valley at the same time when at the source, okay? But when the two waves meet at different locations, then chances are if you are in the middle here at point A, then the two waves travel the same distance to reach point A, okay? So that means when peak comes out, the two sources, they will meet at point A, as the, probably pretty much like when they reach there. If one wave has peak, then the other one will also have peak, right? If one has valley, then the other one will have valley. So at point A, they will add up, okay? Now at another location, rather than in the middle, at point B over here, then wave from source 1 will travel longer distance than wave 2, okay? So then chances are when the wave from source 1 reach point B, if it's the peak over here, then you could get maybe valley from the second wave or maybe peak or maybe something in between, okay? And then also in path C, the same here. So at different locations, they will add up differently because you might not necessarily have the two waves in phase again. That's because they travel along different paths, okay? So in general, if the two waves coming out of the identical sources, they meet in space. If they have path difference of the odd integers, or even number of multiples of lambda, the wavelength, then they will add up, okay, constructed interference. Because then it doesn't matter if you have a peak, the other wave may be traveling like with more path that has another peak meet. So as long as its peak meets peak, it will have them add up, okay? So the path difference will be 0, lambda, 2 lambda, or 3 lambdas. Oh, I'm sorry, just integer numbers of lambdas, okay? So because yeah, 1 lambda is just 1 period already. So just integer numbers of lambdas, and then they will add up, okay? If the two waves, they travel when they meet, their path difference is half of lambdas, then they will cancel out, okay, because that will be distracted interference, okay. So for example, if you have sound waves, if they by two sources, if they arrive at the position that you are hearing the sound, the two sounds, if their path difference is integer numbers, and then you will hear maximum intensity of sound. So that means louder. And then at this point, if they are differ, the two passes are differ by half lambdas, you'll hear destructive interference. That means you'll hear minimum sound, okay, intensity in that case. Now, on the other hand, if the waves by the two sources, they are out of phase, okay, so that means initially when the two sources give out waves, if one gives out maximum in intensity, then the other one will be giving out the negative intensity, the value. So one is having peak, the other one will be having valley, okay? So if that's the original cases, then the interference will be the other way around. So you will hear destructive interference when the passes are differ by integer number of lambdas, and then you will hear constructive interference if the path difference are half lambdas, okay? So you want to pay attention to when the waves, the two sources giving out wave, if they are in same phase or opposite phase, okay? So if they are in phase or out of phase or opposite phase. Sometimes people word it as out of phase, that means opposite phase, okay? All right, so let's take a look on one example here for you to better understand the interference of two waves. So if you have two speakers, they are giving out waves out of phase. So that means at the given instant, if one speaker gives us maximum intensity, then the other one will give you out a negative, okay, of maximum intensity. All right, so then if you are at the middle of the two speakers, you will hear destructive interference because they will cancel out, okay? However, this problem says if these two are separated by 3.5 meters, if you are standing against the wall, which is 5 meters away from the speaker, in the center here, you hear destructive interference. Now you can move to one side, and then you will hear constructive interference because when at this location, then the waves will have peaks meet at that position, okay? So it will be constructive interference, all right? So it's asking you, what's asked here? Let's see. It's asking you what's the frequency of the sound emitted by the speakers. All right. So it tells you the speed of sound is 340. Okay, so that's your speed of wave, 340 meters per second. It's asking you what will be the frequency of the sound. Okay. Now you can relate these two quantities because these two the speed of sound is equal to the frequency times the wavelength. Okay. So then you are looking for the frequency. That means you need to figure out your wavelength. Okay. So then how do you figure out your wavelength here? So the problem says the two speakers are out of phase or in opposite phase. That means in opposite phase. All right. So then if the two sources giving out waves in opposite phase or out of phase, then you will hear constructed interference when the paths are differ by half lambda. Okay, half lambdas. Okay, so you move it to one side. The first time you hear the constructed interference, that means the path difference is half pi. Okay, so the path difference you can write as delta x. Okay, and then you can say this is x1, this is x2. Okay, so delta x will be equal to x1 minus x2. If you don't like it, you can say d1 minus d2 or whatever delta d. Okay, that should be equal to half lambdas. Okay, this is the first time you hear the constructed interference, and then the second time will be 3 halves lambda, etc. Okay, 5 halves, 5 halves lambdas, and then etc. 7. Okay, but we are looking at the first time you hear the constructed interference. So then just take that one. Okay. All right, so you can see you have an equation that has lambda in it, so you probably can try to see if you can figure out lambda there, right? So delta x, x1, x2, we can see here, this is the, if this is the right angle here, then this is 5 meter, right? The height of this triangle is 5 meter. And then this distance you can probably calculate because this is halfway over here. And then you moved by 0.84. So it's half of 3.5 plus this guy, right? This would be this guy, and then this is 5. So then you can use Pythagorean theorem to figure out x1, right? Your x1 will be equal to square root of this will be half of 3.5 plus 0.84. Okay. So this side square plus the 5 square plus the 5 square. Okay. Did I calculate directly? I guess I didn't. So that's fine. X2 then will be equal to this side square plus the 5 square, right? So that will be half of 3.5 minus 0.84 squared plus 5. Okay, because you moved by 0.84 now towards this guy, so it'll be half minus that. So square root. Okay, you can calculate those. But what I did was I just replaced this expression in the place of x1. So I did square root of 3.5 over 2 plus 0.84 squared plus 5 squared, and then minus square root of 3.5 over 2 minus 0.84 squared plus 5 squared. Okay, equals to my lambda over 2. I calculate the left hand side all together. That gives me 0.549. That should be in meters, equals to my lambda over 2. So then you multiply both sides by 2 to solve for your lambda. So lambda is equal to 1.098 meters. Okay. Once you have that lambda, you put it back into the equation of the speed here. You solve for your frequency. Okay. So speed of the sound wave equals to the frequency times lambda. So then frequency equals to speed divided by wavelength. Okay, 340 meters per second divided by 1.098 meters. That gives you about 310 hertz. Okay, that's the sound wave. The frequency of the wave. All right. So this is the case of you have the two sources out of phase. Okay, if you have two sources in phase, then you'll use delta x equal to 0 lambda, 2 lambda, 3 lambda, etc. Okay, so 0, that means you are at the middle. Lambda, it means the first time you hear the next maximum constructive interference either way. Okay, and then the next time. Okay, etc. All right. Any questions you guys might have on this one? Okay. All right. So if you are clear, we can move on then. So as I mentioned, when the two waves meet each other, you basically sum them up algebraically. So that means you can use equation to describe a wave. Okay, so we kind of learned this when we took a look on oscillation last time. Okay, so for oscillation, the motion in x and y direction, you can relate y equal to kind of sine x, okay, a sine function. So for waves, you can write one wave if it's equal to a sine kx, okay, where k is the wave number that's equal to 2 pi over lambda, okay, if you are wondering, but it's a constant number, okay, if the wavelength is given, okay? And then if another wave is slightly different from that one, but has the same magnitude A, okay? You can write it as then, if they have the same frequency or same lambda, then it's kx plus omega delta, okay? Delta is a small number. So if you write the two waves in mathematical like that, then when the two meet, you can actually add them up. Okay, so you add them up, and then it should be equal to a sine. In this case, I think I forgot to include the time dependent of the wave. Okay, so for wave, you can imagine it's going to be position dependent as well as time dependent. Okay, so at different time, different location, you'll see wave differently. Okay, so wave is position dependent, also time dependent. Okay, so for time dependent term, it's minus omega t. Omega is equal to 2 pi times frequency. Okay, called angular frequency. All right, so then the two will add up. Okay, algebraically. So that means you are doing sine of kx minus omega t plus sine of kx minus omega t plus delta. Okay. So a sine function plus a sine function will give you twice cosine of the two angles, differences in two angles by 2 divided by 2, and then also times sine of the sum of the two angles divided by 2. Okay, so that's the one of the trigonometry identities. If you don't remember it, you can actually do a quick review or look it up. Okay. So after you do that, your result will be, if you add the two waves up, it will be equal to, so the cosine the two difference of 2 will be just delta, then divided by 2. Okay, and then the sine you add up to be this guy. Okay, so you have 2 like kx, okay, divided by 2 becomes kx, and then you have 2 omega t divided by 2 becomes omega, but you just have one delta because one with the sine argument has delta, the other one does not have it. Okay, so then it's just divided by 2. Now you can see again, this is a sine function that depends on the position and then the time. Okay. Now in this here, in the cosine function, it doesn't depend on the position and time. Okay. So then it's a constant term here. Okay. So 2a cosine delta divided by t. Delta is the differences of the two sine functions. Okay. Their arguments. So then this is the new amplitude of the wave of the new wave. Okay, then this is the sine of the wave. Okay, so the resultant, if you have delta equal to 0, that means the two are identical. So then cosine of 0 will be 1, the amplitude will be multiplied or doubled. Okay, so amplitude will be doubled. So then you have the two add up. Okay, in the case of delta is equal to 0. So then you can see that's a constructed interference because they add up. Okay. On the other extreme, if the two have opposite faces, that means that delta is equal to 180. Okay. In that case, cosine of 180 divided by 2 will be equal to 0. So then the two wave will cancel out. You'll get distracted interference. Okay. And in between, you'll get a sine function with a new amplitude. Okay. So on this one, let's take a look on this example here. It says two waves with the same frequency, wavelength, and amplitude are traveling in the same direction. If they differ in phase by 90 degrees and each has an amplitude of 4 centimeter, what's the amplitude of the resultant? And then for what phase difference will the resultant amplitude be equal to 4 again? All right, so if you have two waves, they interfere with each other, then so say y1 equals to a sine of kx minus omega t, and then again y2 equals to a sine of kx minus omega t, but with a phase difference. Okay, so this is the phase difference. So part A is asking you if phase difference is 90 degree, what will be the new amplitude, A prime. So in the previous slides, we know that if you have two waves and they add up, then the resultant will be y1 plus y2 equals to A cosine, I think it's 2A cosine. It's 2A cosine delta over 2 times the sine kx minus omega t plus delta over 2. Okay. So this is the new amplitude term, A prime. So you are looking for this. And it tells you A is equal to 4 centimeter. Okay. So you can calculate your A prime. And then in part B, it's asking you, what if your A prime is 4.0 centimeter, then what would be this delta? Looking for the delta. So that's basically the problem, how you understand the problem. Okay. All right, so let's take a look on here. So for the new amplitude A prime, this is 2 times A, 2 times 4.00 centimeter times cosine of your delta is equal to 90 divided by 2. That's in degrees, okay? So you plug in your numbers in your calculator, it's going to tell you it's 5.66 centimeter, okay? So that's your new amplitude if they are differ by 90 degrees, okay? Now, in the second part, your A prime is equal to 4. So you're looking for delta. So then you'll set up A prime to be 4, but this to be still delta. That's what you're looking for. So 4.00 equals to twice of initial 4.00, right? And then cosine of delta divided by 2. Now you're looking for delta. Okay. So 4 and 4 will cancel out. So that will tell you your cosine of delta over 2 is equal to 1/2, right? Because this is 1 here, 2 times 1/2 gives you 1. So then cosine of delta over 2 is 1/2, okay? Now, if you are very familiar with trigonometry, then you will realize that cosine of 60 will be 1/2, right? Sine of 30 will be 1/2, but cosine of 60 will be 1/2. So that tells you delta over 2 is equal to 60 degrees. Or you can do cosine inverse of 1/2, that will be 60, okay? So your delta then is equal to 120 degrees in this case. All right. All right. Any questions you guys might have before we move on? Great. All right. So I think in this case, so we take a look when the two waves have difference in phase, right? So the previous case we took a look on when they have a path difference. Okay, so if they have a path difference, you will end up with interference of two waves. And then if you have phase difference, that means the arguments in the sine function are different from each other. So then you'll have the interference. Now we'll come back later on when we see if the two waves they actually have different frequency. Okay, so the first one we and then the interference of the two if they are having slightly different in frequency. But let's take a look on standing waves, which you guys did lab last week, I think. Yes. All right. So standing waves are waves being confined in a stream or a column of air. Okay, so for example, for guitar strings, so because you have wave confined in the guitar string, so that wavelength has certain frequency. That means it gives out certain tune that you can hear. And for pianos, there are strings inside. Okay, for different notes, then different notes will give out different frequency. Okay. All right. So basically, for if you have a string, then you can make the string vibrate, okay, up and down. Now you can possibly have it vibrate in this fashion, or you can have it vibrate in this fashion, like you have. So the two ends they are fixed, right? So they will not vibrate, okay. But in the middle, you can have vibration maximum. So this is called a note. Let me see. All right, yeah, so over here. All right, so yeah, the two ends are fixed, they are not moving, so they are called nodes. And then in the between here and the center here, you will have maximum vibration that they call anti-node. So this is the first configuration you can have on the stream. Now the second one is you can have the string vibrate in this case, right? So you can have two anti-nodes, okay, 3 nodes there. You can have actually 3 anti-nodes but 4 nodes, okay? So in that case, and then more and more, okay? And you guys saw this in the lab of standing waves, okay, for the same string, you can have different waves in it. Okay, so this guy is called the first harmonic because in this case, this is, if you imagine for a full wavelength, this is just half of it, right? And then you can extend it to another one. So a full wave will include a valley and then the peak, right? So this is half of it. So that means the wavelength on this case will be twice of L. In the second case here, this is a full wave, okay? So then the wavelength is L. And then for the third one, you can see this is the one full wavelength. So then the wavelength is 2/3 of the total length. So you can see for different configurations, the wavelength decreases, okay? Wavelength decreases, the frequency will increase because wavelength and times frequency is the speed, okay? They are inversely proportional to each other. So then the first configuration here will have the lowest frequency possible, okay, for the wave generated in the stream. And then this one is the second lowest frequency. So this is called the first harmonic of fundamental wave. And this is called the second harmonic. This is called third harmonic. So first, second, third referring to their wave frequencies, okay? First lowest frequency, second lowest frequency, third, etc. Okay, in the increasing order of the frequencies. All right. So that's the case when you have the two ends are fixed. Now, for harmonics, it's the same thing here. Instead of having a string, you have a piece of metal that has two ends are fixed. Okay, then when you strike them, they will vibrate. They will give you out the different tunes due to different lengths, right? Because length and frequency are inversely proportional to each other. So, for example, if you look at the first harmonics, then this guy will have higher frequency. This guy will have lower frequency. Okay. Mathematical equation for the first harmonic, the frequency should be equal to the speed divided by 2L. Wavelength will be 2L. And for nth harmonic, so that means higher order, F sub n is equal to n times of the first one. So yeah, so if you have first harmonic, then it will be 1, second harmonic will be 2 times the fundamental, 3 times the fundamental, etc. Now, F1 is equal to V over 2L, so then it's NV divided by 2L, okay? And it's equal to 1, 2, 3, etc. For the wavelength, this is equal to speed divided by the frequency, okay? In this case, could be if you use the fundamental frequency, then it's the fundamental frequency divided by n, the n number of n's, okay? R equal to 2L divided by n. All right, and again, it's equal to 1, 2, 3, etc. And you can summarize that. So if n is equal to 1, frequency is 2L, the wavelength is 2L, frequency will be V divided by 2L, okay, n equal to 2, it's 2L divided by 2, so that's basically L, and then it's V divided by L, okay, etc. from this table. All right, so we will take a look on the example here. This one says a wave traveling on a slinky that is stretched to 4.0 meters takes 2.4 seconds to travel the length of the slinky and back again. What's the speed of wave? Okay, and then use the same slinky stretched to the same length. A standing wave is created, which consists of 3 antinodes and 4 antinodes. At what frequency must the slinky be oscillating? So it tells you that it takes 2.4 seconds. That tells you the time. And then the distance travel, it says travel back and forth. So that should be twice of the length, right? So you can also calculate the speed with distance divided by time takes in that sense for part A. So speed you can also calculate with distance travel divided by time takes. For B, you can sketch the problem. So it says the sense link key, so that's the 4.0 meters in length, L equal to that. It says it has 3 anti-nodes and 4 nodes. Okay, so something like, don't think my figure is correct, but 3 anti-nodes and then 4 nodes. Okay, so this looks like it's going to be a third harmonic. Okay, so if this is L, then this is 2/3 of L. That's the frequency. That's the wavelength. Okay. If you have wavelength, you have speed from there, you can calculate your frequency. So the second one is asking for what's the frequency. All right, so let's take a look on here. I saw several responses there. So the distance travel it says goes back and forth. So that should be twice of the total length, right? The wave goes back and forth in the slinky, so that's twice of that. Divided by the time, 2.4 seconds. Okay, so that's 3.33 meters per second. Okay, for the wave, speed of the wave. And here, so you have your from the sketch, your sketch, you can see the lambda is 2/3 of L. So then frequency, because speed is also equal to frequency times lambda. So then frequency is equal to speed over lambda. Okay, speed is the 3.33 that you got in part A. Lambda is 2/3 of 4 meters. Okay, so that gives you 1.25 hertz for the frequency, right? Yeah, let me know if you have any questions. Okay. And this is what you did in the lab. Okay, so in the lab, basically you have a vibrator, although it's a different, we'll use a different one, but then you have a pulley and then the mass. Okay, so the mass will give you the tension in the string, and that gives you speed equal to square root of tension divided by this mass per length, which is the total length divided by your L. Okay, so we had just look at the two ends of the string being fixed, right? Now, what if one end of the string is fixed and then the other end is open? Okay, so for example, if there's a just a loop here that is kind of attached to the rod here, so then this end can move up and down, okay, as well. Or if you have a case like this, if this end is fixed, then this end is moving up and down. So then This end will be fixed, it's not moving. So this is one of your node, okay, nodes here. Now this end will be your anti-node, okay, you can see that. Now you can extend it to see that. So then there will be a node somewhere here, that's an anti-node, and then there's another node there. Okay, so this is the impossible UI you could have. So you could have a configuration like this. Okay, so this is the first configuration. So then this is only 1/4 of the whole wavelength, right? The length of string will be only 1/4 of it. So your wavelength then will be equal to 4 times of the total length in this case, all right? Now you could possibly create different waves on a string like this. If this end is the node, it's the fixed point, you can have the other end will be the anti-node. Okay, so then you can have a configuration like this. You will have anti-node here, you have node here, and then anti-node here. So in this case, you can see this will be the half of wavelength, but it's equal to 2/3 of the whole string. Okay, so then the wavelength would be 4/3 of the whole string. Okay, then the frequency you can calculate v divided by lambda. Okay, in that sense. This then we call it the third harmonic. Okay, we don't have a second harmonic because the second harmonic will be having this as the node and then the other end as the node. Okay, so that's the second possible harmonic, but because the other end is open, so in this case you only have odd numbers of harmonics 1, 3, 5, 7, 9 because the other end could not be an anti-node. Okay, because it's open, it's moving. So, and then this is the fifth harmonicas, the seventh, the ninth. Okay, so to summarize, the length is equal to m times lambda n over 4. N is equal to 135, the order of harmonics. Frequency will be equal to n times the fundamental frequency, where fundamental frequency is equal to v divided by 4 times of L this time. Okay, so in the previous case, it's v divided by 2L. This time it's v divided by 4L. So that's the scenario when you have standing waves in the stream. Now, similarly, you could have standing waves in air columns. Okay, so this is actually chapter 17.5. All right. So if you have the same bottles, they fill with different levels of water. So then the air column created have different lengths. Okay, so you can line up them up from the longest in length of air column to the shortest one, and then if you blow air on the top, you'll see different tunes produced by those air columns. Okay, so many of instruments will have that scenario, so where the tunes are produced by air columns. Okay, other than like guitar strings. Okay, like drums, flutes, etc. Those are using air columns. Now for air columns, if you have one end closed, the other end open, then you could possibly have standing waves like this. So this is the first harmonic. For the open end, you'll have anti-node. For the closed end, you'll have node. Okay. So again, this is the first, and then the next one will be the third. The next one will be the fifth. So the odd numbers. Okay. So this is similar to the string with one end fixed, the other end open. Okay. And then the same formulas there for the wavelengths and then for the frequency. So this is those equations are the same for a string with one end closed and one end open. And if you have both ends of the air columns open, then you'll get node in the middle for the first harmonic, but the anti-node at both open sides. So for the open side, you always get anti-node. Okay, the next one will be this guy. So this is the second harmonic because you can see this is the whole wavelength. Okay, through the column here, this is the third harmonic. So for both end open, you'll have first, second, third. Okay, so continuous integer numbers of harmonics. Okay, and this is the same scenario when we have the string with both ends fixed. Okay, so those are the same equations as the strings have both ends fixed. I think we'll have to take a look on this later, but just one more note: if you have the air columns, both ends are closed. Okay, so then at the both end you'll have node, and then in the middle you'll have antinode as the first harmonic. You will get similar equations with the both end open. Okay, so just remember, for the both end of the air columns are closed, that's the same scenario as both end are open, but instead you in this case you get nodes on the ends are closed. Okay, antinode in the between, but formulas is they are the same. Okay, for their frequency and wavelengths, that they are the same. Okay, in that case. All right, think I will stop here for today, and then come back for the lecture on Monday.